Hello again. Now we will discuss data modeling. Data modeling refers to how we organize data in a database into tables and how to relate those tables if we want to join them. When it comes to data modeling, the star and snowflake schemas are two common approaches for a warehouse using a bottom up Kimball approach. Schema means to plan or model. So, star and snowflake schemas are models for organizing our data. These data models denormalize organizational data into dimensions and fact tables. Next, we will look at an example to better explain dimension and fact tables in a data model. For example, recall our hypothetical company that sells fancy home office furniture named Bravo. A fact table consists of measurements or metrics about an organizational process. These are known as facts. Each row within the table captures a measurement or metric about one process transaction. For example, Bravo tracks sales order information. Each row an organizational goal. A fact table consists of measurements or metrics about an organizational process. These are known as facts. Each row within the table captures a measurement or metric about one process transaction. For example, Bravo tracks sales order information in a fact table that includes measurements like the quantity of a product sold and the taxes collected for each of Bravo's sales orders. This fact table also includes information about the customer who purchased the product, the date, and the product sold. These values are not quantities on which we can perform mathematical operations, but are foreign keys that allow us to join other tables named dimension tables that provide valuable information and details about the sales order. For example, we can find more information about each customer who purchased an item by joining the sales order fact table to the customer dimension table. Tracking if a customer is a strategic customer is usually not an element of the fact table, but of the dimension table. Dimension tables contain attributes and characteristics that describe the data in the fact table. These characteristics are called dimensions. For example, Bravo's customer dimension table includes customer attributes like name, account number, email address, and mailing country address. It is a reference table. By joining this dimension table with the sales fact table, we can analyze Bravo's total sales by country. This is valuable information because it adds more detail to the total sales metric. We join the fact table with just one dimension table in this example. By joining the fact table with other dimensional tables, such as the product and date dimensional tables, we can analyze the total sales with a larger set of questions. This is what a star schema is. A star schema is an organizational structure that uses a single fact table and one or more dimensional tables. The central table, surrounded by dimensional tables, somewhat resembles a star. The relatively few joins needed for a star schema makes queries fast and easy to use by organizational users. A snowflake schema used by organizational users. A snowflake schema is similar to a star schema. However, at least one of the dimensional tables does not directly join the fact table and must be joined through another dimensional table. For example, if we extend our Bravo star schema by adding another dimensional table for customer countries, the data model becomes a snowflake. This is because we cannot join the country table directly to the fact we could answer more questions. With that, we now know what snowflake schemas. Let's practice what we've learned. In the last video, we reviewed the Star and Snowflake schema data models. In this video, we will review Kimball's four-step process to help us to design these schemas. The first Kimball's four step process to help us to design these schemas. The first step is to select an organizational process for which we want to create a data model, such as invoice and billing, product quality monitoring, and marketing. In each of these processes, analysts and others will want to ask questions about the process and know how well they are performing. Recall that the Kimball bottom-up approach first models one department or business process to create a data mart. In step 2, we decide business process to create a data mart. In step 2, we decide on the grain. The grain here means the level of data stored in the fact table. It's not required, but it is advised that it is the lowest level possible, essentially a level where you cannot split the data any further. For example, if we were building a warehouse for a music service, we should choose the grain level to be individual songs versus a full album from a band. If we were tracking shipping data, we should store the individual line items of a shipment versus the overall shipment. This would allow the organizational users to analyze the data to ask questions like, which song is the most popular? Or which products were delayed the most in shipping? Organizational users may be unable to answer the questions they have if we choose the wrong grain here, making the info and data warehouse less valuable or useless to them in extreme circumstances. In step 3, useless to them in extreme dimensions that apply to each fact table row. Overall, we want to add a rich set of dimensions representing as many characteristics as possible of the fact table data. A data model may have a unique set of dimensions, but there are some that are typically used. For example, tracking the year, month, and quarter is typical for any process that involves time. Likewise, tracking the address, state, and country is common for any process involving location. Also, it is standard to include the dimensions of name and email address for any process involving users. Answering the question, how does the organizational users describe the data that results from the business process helps in this step. Also, it would be valuable for us to have feedback from analysts and other users who often work with the data. In step 4, and other users who often work with the data. In step 4, we want to identify the numerical facts that will populate each fact table row. Examples of possible facts for a fact table for a music service include the total number of plays or sales revenue for a song. However, if we were creating a fact table for a ride sharing service, examples of possible facts are the distance traveled or time needed. These facts capture a measurement or metric of the process. Having members of the organization answer the question, "What are we answering?" will help us identify numerical facts to include. Recall, the purpose of the data warehouse is for reporting and analysis of the organizational process. We will need to decide on a vital numerical measurements to store to answer likely questions about the process later. Finally, the fact warehouse is for numerization facts tracks typical items of a shipment versus the overall shipment. By the numerical facts or sales revenue for a song. However, if we were creating a fact table for a ride sharing service, examples of possible facts are the distance traveled or time needed. Having help us identify is for a decide process later. Range selected for our star or snowflake schemas. It is vital to work with Hello again. We will continue our discussion of data modeling by reviewing Kimball's approach to modeling slowly changing dimensions. It should be noted that there is a modern approach to this challenge, but we will review first the historical standard approach. Okay, let's start our discussion. Over time, some values in our dimensional tables will need to be updated. For example, imagine we are working on a data warehouse that needs to be updated. Over time, some values in our dimensional tables will need to be updated. For example, imagine we are working on a data warehouse for a used car dealership. We have a record in our product dimensions table for Tesla's Model Y. It was initially classified as an electric vehicle, but now we want to update the value to something more descriptive: electric crossover. There are three solutions for this problem: type 1, 2, and 3. This only applies to dimension tables. The values of the metrics captured in a fact table should stay the same over time. For example, suppose we are capturing revenue in a fact table. In that case, the total revenue for a company last year should stay the same over time, excluding capturing the correct data initially. The Type 1 methodology updates the row's value data initially. The Type 1 methodology updates the row's value to the current value. This will update the value for any new reporting, but it also erases any history of the previous electric vehicle value. If we rerun any historical reports, this car will now show under the electric crossover category. Therefore, these historical reports will not match the original values. In some situations, this will not be acceptable. The reproducibility of reports is often an important requirement for organizations. In Type 2, we add a new row for Tesla to the dimension table with a new ID and the updated category value. This will allow us to maintain any historical reports because those historical records in the fact table will reference product ID 12345 in the dimensional table, and any new records in the fact table will reference 20053. Finally, we can add columns to track the start and end of when the values are in effect. Now that we have looked at types 1 and 2, let's look at type 3. With type 3, we add another column to the dimension table to capture the previous category. So, we set the value of the past category to electric vehicle and update the category to the new value of electric crossover. We will reference the past category column in the dimension table if we need to rerun a historical report. This approach supports looking at both a current and historical view simultaneously. However, this may require updating the coding for historical reports, and we are limited to tracking 2 historical changes in this setup. In theory, we can add more columns to track more changes. Additionally, we can add a column to track the date on when we change the category. We have now reviewed the 3 standard Kimball approaches to slowly changing dimensions. However, there is a modern approach. To slowly changing dimensions. However, there is a modern approach. However, review the three standard Kimball approaches to slowly changing dimensions. However, there is a modern approach. A modern approach takes advantage of the low storage costs by saving snapshots of the entire dimensions table. We would update the value of the dimensions table similar to type 1, and the warehouse system stores snapshots of the current state of the dimension table. Therefore, when we run historical reports, we use the dimension snapshot that was current at that time. Typically, dimension tables have significantly fewer rows than fact tables, and storing duplicate copies of tables is a manageable task for modern hardware. Okay, let's practice. Welcome back. Let's now turn our focus to column and row data storing. This subtle difference in how data is stored allows for tuning of databases for transactional or analytical workloads. We want to optimize our queries for speed, and with the data warehouse, we often work with analytical workloads. Recall our discussion of OLAP versus OLTP systems in the previous video. In this video, we will learn that the column store is best for analytical queries. Let's look at some basics to understand this better. In analytical queries, let's look at some basics to understand this better. In an oversimplification of the process, we can say that computers typically store data in blocks on their hard drive for long-term storage. This data can be stored over multiple blocks. When that data is needed later, the hard drive looks up which blocks hold the required data and reads those blocks. Data stored over many blocks will take longer to retrieve than the same data stored over only a few blocks. For analytical workloads, we can take advantage of this by storing likely needed data over only a few blocks, increasing query speeds. Let's take over only a few blocks, increasing query speeds. Let's take a look at an example. The data for this table is downloaded from the US CDC and contains flu infection data. Each row includes the hospitalization percentage by age group during a particular season. Now, let's look at store format. Each row of data is stored together. Now, let's look at how this data is stored with row store. If the table is written in a row store format, each row of data is stored together. To illustrate, all the data for the second row in our table is stored together. In our diagram, we place the data for the 2019 season's 18 to 49-year-old group in block 2. This format is excellent for transactional workloads because the computer system can add new data to the table for the 2019 season. What is the average hospitalization data for blocks of data, where we often want summaries of many rows of data. In comparison, the column store format stores the data for a column together. For instance, the data for the age group column is now shown in block 2 of the diagram. Answering the question, for the 2019 season, what is the average hospitalization percentage across all age groups? The computer system only needs to read the blocks with the answer to this analytical workload. The trade-off is in data is stored together in blocks in the row store format. Also, it is ideal for transactional workloads. However, with column store, entire columns are held together in blocks. Thus, it's best suited for analytical workloads and has better data compression. It's practice time. Analytical workload. And has better data compression. It's practice time. Hey, and welcome back. In this video, we will revisit the data integration process of ETL and compare it to a similar technique called ELT. We can use both methods for integrating data in a data warehouse. ETL and ELT begin with extracting the data, and both load and transform data, but the orders are different. In an ETL process, the data is transformed and cleansed, then loaded into the data warehouse. In comparison, ELT stands for extract, load, and transform. In this process, the data is extracted, loaded in the data warehouse, then transformed. The overall goal for both methods is to end up with cleansed data that we can use in the data warehouse, but the order of steps they take is different. The key to the ELT process is that the data is loaded before being transformed. We will review this more shortly, but first, let's look at the ETL process again. With the ETL process, the data is transformed as it moves from the inputs to the warehouse. This process requires organization to the warehouse. This process requires organizations to use a cloud-based service or purchase the software and computer servers to run it themselves. Overall, the ETL process requires a separate system from the data warehouse to perform the transformations as the data moves. A couple of pros using an ETL process come about because the data process only delivers clean and transformed data to the warehouse. First, ETL tends to have lower data storage costs than ELT because it only keeps copies of the transformed data. Secondly, meeting compliance security standards on PII, or personally identifiable information, is more manageable. We can omit PII data in the source systems before loading it into the warehouse, so sensitive data will never make it into our data warehouse. And many ETL tools are certified to meet government PII security standards. However, there are a couple of cons to using an ETL process. First, we do not store the original data from the input sources during the transformation process. Therefore, any errors or changes to the transformation logic mean pulling the data from the source systems again. It can be challenging to find the time to pull large batches of data from the systems without slowing them down. Additionally, there are costs related to the ETL's separate computer system. However, costs related to the ETL's separate computer system. However, the ELT process extracts data from the sources and loads full copies of that data into the data warehouse. Then, the resources and software of the data warehouse are used to transform the data. Afterward, the transformed data is then used as usual for the data warehouse. Some pros of the ELT process are no need for a separate computer system for the transformation process. Additionally, we can rerun the transformation process without impacting the source systems. Finally, it is often used for near real-time situations because the amount of time needed to load the data is not connected to the complexity of the transformations in the ELT process. However, Cons include the need for more storage to hold the copies of the original data. Also, additional considerations are needed to comply with the security standards if the data sources contain PII data. The data sources contain have grown in popularity due to an upcoming video. Still, for now, the cloud allows an organization to store a near unlimited amount of data with access to vast computing resources. This means an organization is not limited by storage and can process the transformations faster using parallel computing power. Okay, time for some practice. This video will review some common transformation steps during the ETL or ELT processes used to clean the data. In this video, we will shed more light on each in this list. This is a partial list. When implementing the data transformation process, the implementation team will evaluate the organizational requirements and use a combination of these four processes and others to meet the needs. First, we will review data format cleaning. The data warehouse receives data in all types of formats. For example, values of dates or names might be abbreviated, have different capitalization, or be formatted differently in the input sources. However, at the end of the transformation phase, we want clean and consistent data for the data warehouse. Therefore, it is essential to use organizational rules to format the data so that the output is consistent. Let's look at some taxicab user data to add more context. In it, we have data from two sources that we want to join together. Unfortunately, with the first table, the capitalization of the user's names is inconsistent. Also, the date format in the other table is not what we want, so we cleanse the data by adjusting both formats in the final join table. Parsing addresses is another format in the final join table. Parsing addresses is another typical cleansing operation. This process takes an address and divides it into its individual components, like city and state. This helps standardize the data. Additionally, many ETL tools can automatically perform address lookups and validate the address. Next, let's do address lookups and validate the address. Next, let's discuss data validation. Two common validation checks include range and type checks. First, range checks to see if the data values are in the proper range. For example, you would not expect to see a person's age entered as 300 years old. This will fail the validation check. Another validation check looks at the data type of the value. For example, imagine that the data type of the value. For example, imagine that the data from our source system return a data type of string for customers' ages. Normally, we would expect an integer data type. Therefore, the type check. However, it is best to fix these issues in the input source if it can be used. Finally, the deduplication step removes repeated rows of data. In this example of hospital doctor data, we have two tables. We want to append the rows on the left to the bottom of the table on the right. However, we do not want duplicate rows. Deduplication will flag that Dr. ID 275 is a duplicate and will only append rows 300 and 310. In summary, we review 4 different data cleaning processes that can be done in the ETL or ELT step. However, an organization with a strong data governance program should reduce the need for some of these cleaning processes. Data governance looks to develop rules and definitions around the data and detect and correct the data that deviates from its definition. Therefore, by the time it gets to the ETL or ELT process, less data cleaning needs to be done. Okay, let's review. Hello again. This video will discuss the options for implementing a data warehouse on-premise located within the organization's physical confines or in the cloud. When implementing a data warehouse on-premise, organizations purchase the servers and computer hardware and install all the necessary software at some physical location within the organization. There are several benefits for doing this. First, in the organization. There are several benefits for doing this. First, it offers an organization maximum control and customizability over all aspects of the warehouse's implementation and ongoing maintenance. With complete control, organizations could implement strict governance of the data and who has access to it and implement. Additionally, since the warehouse is likely on the organization's local network, they can leverage their local network speeds for data transfers with other organizational systems and avoid some bandwidth challenges of the cloud. Finally, they can tune the warehouse for optimal performance for the organization's workloads. However, on-premise requires purchasing the equipment upfront. This includes data warehouse cloud services. Over providers, due to these challenges, many organizations have looked to cloud providers for support in implementing their data warehouses. Over the last few years, there has been a rapid rise in the use of cloud services. Some cloud data warehouse providers include Amazon's Redshift, Microsoft's Azure Synapse, Snowflake, and Google's BigQuery. Gartner, the consulting firm, predicts that by 2026, public cloud spending will exceed 45% of all enterprise IT spending and is forecasted to be greater than $482 billion. Many cloud providers offer a data warehouse as a managed SaaS or software as a service. In this case, the cloud provider takes care of software additional resources to compute a challenge workload. Organizations anticipate a significant spike in the warehouse usage. This might lead to unanticipated high costs for the organization. Finally, organizations may implement a warehouse using a hybrid approach where they operate a data warehouse on-premise and in the cloud. One reason for doing this is for a backup or disaster recovery. In summary, an organization for a backup or disaster recovery warehouse if they need complete control. However, cloud implementations offer many benefits. In particular, not having to manage the software and infrastructure and the ability to scale as needed. Although these benefits come at the price of complete control, they should understand the strengths of each implementation practice. Welcome back. This time we will walk through a data warehouse design example. Let's give context for our hypothetical example. We work for a new company, a startup, that has developed a popular photo sharing app. Photographers use the platform to sell their photos. Our role is to design and deploy a data warehouse for the company. As a startup, we must show business a data warehouse for the company. As a startup, design, photography, a startup context. This time we will walk through a data warehouse design example. Let's give context for our hypothetical example. We work for a new company, a startup, that has developed a popular photo sharing app. Photographers use the platform to sell their photos. Our role is to design and deploy a data warehouse for the company. As a startup, we must show business results quickly. There are many strengths of a top-down approach, but the implementation time tends to be longer versus a bottom-up approach. Therefore, we decide on a bottom-up approach. Additionally, the sales group was flagged in our requirements gathering as the priority for the data warehouse. Next, we need to start modeling our data. Since we chose a bottom-up approach, we will likely use a snowflake or star schema, and we can use Kimball's 4-step process to design the tables. In step 1, we need to select the organizational process. Our requirements gathering uncovered that the sales group is trying to understand better what type of customers purchase photos from the app. In addition, the sales group would like to analyze the data to prioritize which customers they reach out to. Therefore, we will focus on building a fact and dimension table that tracks customer purchases. In step 2, we declare the data grain. In this case, tracking each purchase by a customer as a row in the fact table will provide the most flexibility. Additionally, it is the lowest level of detail for purchases. Next, we identify the dimensions we will track. Again, we are trying to prioritize customers. We think about how other users describe the data that results from the sales group prioritizing customers. Some important features are a customer's location, joining date, and default payment method. Additionally, we will have a dimensions table for photos and dates that we won't detail here. In step 4, we want to identify the facts. To determine how much time these features, after finishing the 4 steps, we have our fact and dimension tables. In our simplified example, we only have schema data to make is whether to implement our data warehouse on-premise or infrastructure. A cloud. Finally, we must decide if we use an ETL or ELT process. The organization. Additionally, on call. We completed many critical planning phase for designing allow us to Outstanding! You have made it to the end of this course. We started by covering some of the basics of data pairs to data different layers of an OLAP dimension tables process. However, a few things we did not cover include digging into SQL fundamentals, building data pipelines, or analyzing the data warehouse. If you want to learn more about these topics, items or books you might enjoy.